Smoke is going to take us, we've been looking at the macrocosm and going outside of the domain of human sense perception into the macro domain. Quao is going to now take us into the micro domain, beyond sense perception into the very small and the universe that opens up to our imaginations as well. Look well.
Hey, hello. I'm going to give a presentation about nuclear energy. It's going to be not too detailed, hopefully. Try to keep in the generalities. If at any time you have a question, I would very much appreciate if you can just stop me and ask your question so we can have some sort of discussion. I think it can be more fun than just me dumping a lot of information to you. Okay, so I'm going to start from the very beginning. I want to make clear what's the difference between a chemical reaction and a nuclear reaction. So here I have, let me just put a nicer thing here. Here I have a simplified diagram of an atom. So we have the nucleus in the middle and the electrons around of the nucleus. So this whole thing, the nucleus plus the electrons, is what we call the atom. The thing in the middle is the nucleus. So as you can expect, the nuclear reactions deal with the nucleus. If we put two atoms together, we can form molecules. Two or more atoms together, we can form molecules. And molecules are attached to one another through chemical bonds, which happen through sharing of electrons. So all of the molecules, they all have to deal with electrons around of the nucleus. So the nucleus doesn't really interfere in molecules or chemical reactions. So I have here a simple description of a very common chemical reaction, which is the burning of methane. So this molecule is methane, natural gas. So we have carbon bonded together to 4 atoms of hydrogen through chemical bonds, reacts with a molecule of oxygen, and creates CO2 and water. So we have different molecules when we start and when we finish, but the atoms are the same. So we start with carbon, oxygen, and hydrogen, and we finish with carbon, oxygen, and hydrogen. So this reaction will liberate a little bit of energy. And here I wrote the energy in terms of electron volts, which is what we usually use for like very small amounts, like 1 molecule or things like that. Now, if we try to represent a nuclear reaction in the same way, it would look something like this. So we have a atom of uranium. It fissions and it becomes different atoms. In this case, barium and krypton. This is a fission reaction. We have another type of nuclear reaction, which is a fusion reaction. So in this case, we have 2 atoms of hydrogen. This is a special type of hydrogen that is called deuterium, but it's still hydrogen. They react together, form a different atom, in this case helium. So you can see that the nature of the atoms change. And these atoms can be inside molecules, but it doesn't really matter for the nuclear reaction what molecules these atoms are in. I also put it here, the energy output of these types of reactions. So for the fission reaction, it's about 200 million electron volts for 1 uranium atom fissioning. And the fusion reaction, so in this case, the deuterium-deuterium reaction, is about 2 million electron volts. So you can see already that the amount of energy liberated by a nuclear reaction is way, way higher than a chemical reaction. Now I mentioned here fission liberates energy and fusion liberates energy. So that can be a little bit confusing. How come splitting an atom liberates energy and then fusing it together again liberates energy? There seems to be some sort of loophole here where we could just like take an atom, split it, liberate energy, fuse it back together, liberate more energy indefinitely. Well, that wouldn't work. And I'm going to explain why. So I have here a very simple representation of a nucleus. So nucleus is made of protons, which are positively charged particles. And if we have only protons, they won't be able to stick together because they're repulsing one another. So nucleus have neutrons. And the neutrons, they're not charged. And they're used kind of like as a glue inside the nucleus to hold the whole thing together. And different nuclei will have different stability. So depending on the size of your nucleus and the amount of protons and neutrons, your nucleus can be more or less stable. And so I have a graph here representing the stability of different, or basically all of the atoms that exist. You don't have to understand here the units, the average binding energy. You just have to know that the higher it is, the more stable is the nucleus. So on the left side of the graph, I have the light elements like hydrogen, deuterium, helium, lithium. And on the other side, on the right, I have the most heavy elements like uranium. And in the middle, I have the most stable elements. These elements are around the atom of iron. So if I start with these type of elements here, and I fuse them together to create something heavier, the result is going to be more stable than the thing that I started with. And that process will liberate energy. So this is a fusion reaction, and it liberates energy because the products are more stable. On the other side, if I take very heavy elements like uranium and fission them, split it into two lighter atoms, each of them being more stable than the uranium, then this process also liberates energy because the result is more stable. So this is why both fission and fusion can liberate energy, because we start with different elements, but we go towards elements that are more stable. So now I'm going to focus more on the fission reaction, which is the way the current nuclear reactors work. And I'm going to give you an idea of how these things work. So this is a representation of a fission reaction. This is a nucleus of uranium. So the fission reaction is triggered when we shoot a neutron at it. Fission reactions do not happen like that just spontaneously. Well, they do a little bit, but it's very, very rare. We have to trigger them. And to trigger them, we have to shoot a neutron. Once the uranium absorbs a neutron, it will split into two smaller atoms, which are called fission products. It's going to liberate a lot of energy, and it's also going to produce new neutrons. These new neutrons are going to travel around the material and counter another atom of uranium. It's going to split this new atom of uranium, liberate more energy and more neutrons, and the cycle starts again. So we have here a chain reaction, and this is what powers the nuclear reactors. So this thing here produces heat in our material. Now, what we want at the end is to produce electricity. So we want electricity to power the cities and the industry and everything we use. The electricity itself is produced in a generator, which is made of a big magnets and things that turn. This thing is turned by a turbine, which is powered by steam flowing through it. And the steam itself is produced by the nuclear reactor. Okay, so now we have narrowed down the task. We have to use the energy produced by a fission reaction to boil water. Okay, so how do we go about it? Let's say you're giving the task of boiling water with uranium. So we're going to do it in a very simple way. We're going to take a big tank of water and put inside a big block of uranium. This big block of uranium is big enough to sustain the critical chain reaction. So inside at the microscopic level, we have a lot of these reactions happening. This is going to heat up the material, and through the surface of the block is going to warm up the water. The water is going to become steam and turn a turbine, etc. So that would work, but first of all, the heat that we transfer to the water is very little because it only goes through the surface. And in the middle, the thing is going to become so hot that it's going to melt. So it's not the best way. It's better if we take that block and cut it into a lot of thin tubes like this. This way, the heat is taken away from the water with more surface contact, basically. So the tubes are not going to heat up and melt, and we can transfer more heat to the water. So this is essentially the way normal reactors work. So it's a big vessel of water with a lot of uranium tubes inside that transfer the heat to the water. The real ones look a little bit like this. So we have every square thing here is called a fuel assembly. This is one fuel assembly. Every fuel assembly has 17 by 17 tubes. These tubes made of a special metal. Inside of them, they contain the uranium. So this is uranium. It's in this picture, it's in the form of ceramic. So it's uranium oxide, which is what is usually used. And this is the way almost all of the reactors around the world work. Reactors in Canada are a little bit different, but I'm not going to go in the details of that in this presentation. But it's also just water and tubes. So this is a picture of a nuclear power plant in the US. This power plant produces about 2,300 megawatts. To give you an idea of how much power that is, Montreal on average, if we average all the energy consumed in 1 year, it's about, the city of Montreal consumes about 3,500 megawatts. So basically 2 of these reactors can power the city of Montreal. Now I put these letters here because I want to ask you a question. I want people to tell me where do you think that the reactor is, the actual place where the fission happens. Where is it? Maybe Matt, you can unmute the phone. Yeah. So where is the nuclear reactor? D, okay, C. Okay, okay, so you guys are smart. Yeah, it's actually C. A lot of people think that the reactor is in these big towers. But it's actually in C, so, and it doesn't take the whole building. So inside this building, which is called containment building, the reactor is the red thing here. So this is the vessel of water with the uranium tubes inside. A lot of people think this is the actual reactor. I don't know why this is associated with nuclear power. This is a cooling tower, and its purpose is just to cool down the water coming out of the turbine. And inside it looks like this. So it's empty. This is an abandoned one, so it doesn't have a lot of machines, but it's essentially empty inside. And it's made in a special shape to have the steam flow very easily. Nuclear power plants are not the only ones that use cooling towers. So this is a picture of a coal-fired power plant. You can see it has 8 of those cooling towers. There is no nuclear reaction happening here, it's just burning coal. The coal is here, as you can see this black stuff here. These are mountains of coal. a coal-fired power plant of 1,000 megawatts, so about the power of a reactor, it needs 90 train cars like this one every day to be able to run. It uses tremendous amounts of coal. Now, what about nuclear power? Like, how much nuclear fuel does it use? So we have here a 1,000 megawatts coal-fired power plant. It uses 900 tons every day. Now, a 1,000 megawatts nuclear power plant uses 25 tons every 1.5 years. So that's a big difference. And actually, they're not refueled every day. So to refuel a nuclear power plant, you have to shut it down, open it, take 1/3 of the fuel out, put in fresh fuel, close it, and then turn it back on. So there's so much energy in uranium that they can do that every 1.5 years, and it works pretty well. So if we dilute this amount to have a number per day, we get here to 0.05 tons per day. So you can see that there's a significant, tremendous difference between the fuel, the energy density inside the uranium. So I want to talk a little bit more about that energy density, and I'm going to bring, sorry, I want to bring back the camera. Okay. Okay, now you can see me. I have this piece here. So this piece of metal, it's not uranium, unfortunately. This piece of metal is lead, which is a heavy metal, just like uranium or thorium. Uranium and thorium are also metals, and they're pretty heavy. Uranium is actually heavier than lead. So this amount of uranium here, if it was uranium, is about 300 grams. Put in a special type of advanced reactor, this amount of uranium would produce enough energy to basically power your whole life. So 80 years of average North American lifestyle is contained inside this amount of fuel. So you're probably thinking that uranium must be super expensive if it has so much energy inside. So it turns out that, let me put the thing again. It turns out that the price of uranium is about $25 per pound. It's pretty cheap. So this piece that I showed you would be around $20. Yeah, it's very cheap. It's basically a very good deal. And nuclear power plants spend very little money on fuel. All the money they use, it goes into building the reactor and operating it, maintaining it, and all of that. So I want to give a few more examples on how dense this thing is. So I have here a ton of coal. So inside coal there are impurities. There are many types of impurities. One of them is uranium. Actually, there is a little bit of uranium in coal. 1 ton of coal contains about 2 grams of uranium. If we take these 2 grams of uranium and fission it in an advanced type of reactor, we get more than 5 times the energy that we would get by just burning the coal. So there is more energy in the impurities, uranium impurities in coal, than in coal itself. This basically tells us that the uranium is not a rare material. There's uranium a little bit everywhere with lower or higher concentrations, and uranium mines are basically places where the soil has a lot of uranium and it's worth it extracting it from there. So coal is not a good source of uranium because it doesn't have that much uranium. Another shocking example is now with deuterium. So deuterium, as I said earlier, is a different type of hydrogen. So water contains hydrogen, and in seawater, the hydrogen in the water of seawater a small portion of it is deuterium, which is a different type of hydrogen that can actually be used to power a fusion reaction. So 1 liter of seawater contains about 35 grams of deuterium. This amount of deuterium, if we put it through a fusion reactor, extract all of its energy, it's as much energy as 370 liters of gasoline. So that's a tremendous amount of energy. So imagine if all the oceans were actually made of gasoline, and 300 times that amount of energy. So basically, we don't have any sort of resource scarcity problem. We only have a problem of lack of technology. Now, I want to talk a little bit about nuclear waste, because most of people, when they hear about nuclear energy, the first thing they think of is nuclear waste. So when we have a reactor, like a normal reactor that I showed you earlier, we put in a new fuel. It's 100% uranium. It stays in the reactor for about 3 years, one and a half to 3 years. When we take it out of the reactor, we've only used about 3% of the uranium. The 97% of it, it's still either uranium, like the initial uranium, or plutonium, which also liberates energy. And it has also some other little things. So these fission products, just to remind you, they're the thing that comes out of the fission reaction. So we have the uranium fissioning happening, and then the things that it's split into, they are the fission products. So they only make up 3% of what we call waste. And this thing is a little bit complicated to handle because it's pretty radioactive. So what they're planning to do in Canada and most of the countries is just to build a deep geological repository. So they encapsulate the fuel in special containers, and they put that underground in special locations that have no earthquakes or things like that. And they do all sorts of calculations to make sure nothing is ever going to happen to those encapsulated nuclear waste. So that would work. It would work pretty well. But if we really don't want to produce any waste, we can actually do it. And we can do that with a different type of reactors called breeder reactors. So I'm not going to go through the details, but basically the breeder reactors have to be coupled with the reprocessing factory. And through different cycles, we can use all of the energy contained in the uranium. And the only thing that comes out as a waste are the fission products. So doing it this way, with the same amount of fuel, we produce 20 or 30 times more energy. And more importantly, the type of waste is different. The fission products are not radioactive for such a long time. So a couple hundred years is enough for them to decay. And some isotopes are actually valuable. They can be used for different applications. And also, if we have a certain isotope that is very problematic, that we don't want to bury underground or anything like that, we can put it back in the reactor, in this type of reactors. And inside the reactor, sooner or later, is going to absorb a neutron and be transformed into something else that is less problematic. So basically, with these type of reactors, we are capable of essentially getting rid of the nuclear waste problem. And these are not some sort of futuristic dream reactors. They actually exist. This is a picture of a breeder reactor, a sodium-cooled reactor in Russia, and it's been operating for a few years. So I said sodium cool reactor because it doesn't use water. So let's go back to our simple little reactor here. I said that most of reactors use water here and tubes of uranium. So this is true for most of the reactors, but it doesn't have to be like this. So this thing here can be another type of fluid, like gas helium, or it can be a liquid metal like lead or sodium. It can be a molten salt. And the fuel itself, it doesn't have to be tubes. It can be pebbles, or it can even be liquid. Also, it doesn't have to be uranium. There's another nuclear fuel called thorium. There is more abundant than uranium, and but it's more complicated to use because we need to use those types of advanced breeder reactors. So the point that I'm trying to make here is that there are a lot of possibilities to test, and we've only tested one, which is water with solid tubes, but we have to test a lot of other things and see which one is better, because using those different types of materials give advantages, like having reactors that are inherently safe, that can produce higher temperatures to do things that we cannot do with normal reactors. They can be breeder reactors, things like that. So nuclear energy is very much still in its infancy, essentially. Okay, so I hope by now I have more or less convinced you that nuclear power is a very good way of producing electricity. But some of you might be thinking, well, in Quebec, we have hydroelectricity. It's very efficient. We have a lot of water. It's cheap. In our case, we don't need nuclear power. Well, the thing is that nuclear power is not only for boiling water. We can do a lot of other things with nuclear power, and that we cannot do without reactors. So I'm going to go here through some of the other applications that go beyond producing electricity that we can use reactors for. One of them is medical isotopes. So in modern medicine, we use different types of radioactive isotopes for different purposes, like diagnosing different specific types of diseases or specific areas in the body, or treating special cancers, things like that. So there are a wide variety of medical isotopes, and all of them have to be produced in a nuclear reactor. Another application is neutron activation. So this is a method for analyzing materials. So basically you take whatever sample you have, you put it inside the reactor. It's going to it's going to be submitted to a lot of neutrons. It's going to become a little bit radioactive. You take it out of the reactor, analyze carefully its radioactivity, and then from that you can know exactly what elements you have in your sample and what amount of each of them. There are other things you can do with neutron activation, like, for example, people who study the flow of water in rivers and things like that. They can put a little bit of water in the reactor, make it slightly radioactive, then put it back in the river. It's very small radioactivity, so it's not dangerous. You put it back in the river, and then with Geiger counters, you measure the reactivity downstream in different spots, and then you can precisely know where the water goes through. There are a lot of applications for neutron activation. Another thing is neutron imaging. So this is similar to X-rays, but it can see things that X-rays cannot see. So, for example, metals. X-rays cannot easily penetrate metals, which neutrons can. So in this picture here above, we have, these are blades of a jet engine. Inside the blades of a jet engine, there are a lot of channels used to circulate air to keep the blade cool. And for quality control, they have to check if all these channels were properly manufactured, and they cannot do that with X-rays. So they have to use neutron imaging for this. Another particularity of neutrons is that they're capable of penetrating metals, but at the same time, they're very sensitive to some specific elements like hydrogen or boron or other elements. So in this picture here, we have flowers inside a very thick lead container. And this is the neutron image. So the neutrons easily cross through the lead, but then can very well photograph kind of the flowers inside of the lead. So this is a very good technique for like non-intrusive, non-destructive scanning methods. Also, more generally, like when we develop nuclear technology, we are forced to increase our understanding of physics. More people have to study physics, and basically this is a very big advantage to society in general when we are forced to study how the particles work in how nature basically works in its more fundamental way. Another very interesting application is a plasma torch, and this is more related to fusion reactors. So let's say we want to get rid of waste, not nuclear waste, but just the normal waste that we put in landfills. We could do it with plasma torches. And to do that, we would like basically throw all of the waste through a torch. That torch will heat up the waste, turn it into a gas, and heat it up even more to turn into a plasma, which is some sort of gas that we're capable of manipulating with magnets and electric fields. Once it's in that state, we're capable of separating element by element the waste. So we can retrieve all the elements separately and form raw materials back from the waste and recycle basically anything that we put through the torch. So plasma torches exist already, but they're not used for that application that I just mentioned. They're used for like welding and things like that. It's also possible to treat waste with it, but they cannot make them hot enough to make plasma out of the waste. They just vaporize the waste and melt like the metals and things like that. So to recycle really everything and separate the elements, then we would really have to master fusion technologies, which is a very similar technology. It uses plasma as well. So this is one thing that we could do if we develop our nuclear technologies. And finally, and very importantly, space exploration. So we are very limited if you want to do space exploration and don't use nuclear energy. We are very, very limited. And I'm going to mention two areas where nuclear energy is very useful when it comes to space exploration. So one of them is propulsion. Propulsion is usually done with chemical reactions, so usually hydrogen and oxygen reacting together, producing flow of gas exiting the rocket, and that flow pushes the rocket forward. So the maximum speed at which the rocket can go is basically the speed at which, or proportional to the speed at which the exhaust comes out of the rocket. So for a chemical reaction like hydrogen and oxygen and certain geometries, that speed has a limit. And the limit is not very high. So basically, if we want to go beyond the moon with chemical rockets, we have to wait very, very long times. It's not very practical. We can use nuclear power to power rockets, and there are different ways of doing that. One way, which is the simplest, would be to use what's called a nuclear thermal rocket. So this works very similarly to a chemical rocket. So we still have a gas that we're going to heat up, but instead of heating it up with a chemical reaction, we heat it up with a nuclear reactor. So we can attain higher temperatures, and the gas can be evacuated at higher speeds. So we can actually go 2 to 3 times faster with these types of rockets. These have actually been investigated in the US back in the 60s or 70s. They even built some of them and tested, not like in a real rocket, but on the ground. So this thing works. It's just a matter of like putting money back into it and developing it. Other types Another one is like an ion thruster. So in this case, the nuclear reactor on the ship is used to produce electricity, and then this electricity is then used to accelerate ions. So ions are like atoms, but they're lacking electrons, so they're charged. So because they're charged, we can accelerate them with an electric field. And we can accelerate them to a very high speed because they're very light. So that gives us the possibility of having spaceships that can go very fast. They might speed up very slowly, but their maximum speed can be very, very fast. There are many other types of, there are many other designs of nuclear propulsion systems. Here I just listed two for fission. And we also have fusion, which it's still under early developments, but if it works, it would be really, really great because the density of the fusion fuel is even greater than fission. So we can carry a lot of energy in a small load. So in a fusion rocket, we will have the fusion happening, and then the products of the fusion reaction are the things that we are projecting out of the rocket. And because they have a lot of energy, those particles will be projected at a very high speed and would give a very quick acceleration. Okay, so this is for propulsion. Now, if we build like a colony or something like that on the moon or on Mars, that colony will have to use materials. We'll have to use like water, oxygen, hydrogen, probably materials for construction like steel, aluminum, things like that. So it wouldn't be possible to like bring all of these materials from the Earth with rockets all the way to the colony. It's not practical. What would be feasible though is to bring one time a nuclear reactor, and then that nuclear reactor is used to produce a lot of energy, and then that energy can be used to basically take the rocks of the place where we put the colony and turn these rocks into whatever material we want by extracting the elements that we need. Because usually there is, all the basic elements are found a little bit everywhere, but they're not necessarily in the form that we want them. So it's just a matter of using energy to turn them back in the form that we want them. So this is pretty much the end of my presentation. I hope I have managed to transmit you the idea that, well, first of all, the nuclear power is still at a very early stage. We still have a lot of things to try and to develop. And most importantly, nuclear power is something that is absolutely necessary for a society to progress. There's no future without nuclear power. So thank you very much, and I'm now ready to answer any of your questions. Yeah, pebble bed reactor is one of the hot topics right now, kind of. So usually pebble bed reactors, let me go back to the, okay, let me share the screen again. So here, pebble bed reactors, instead of having here a lot of little tubes, it would be pebbles. So like a pack of a lot of pebbles. And usually it's gas flowing through the pebbles. So there is like, there would be like a lot of space around the pebbles so the gas can go through. And the gas will pick up the heat around the pebbles. And then the gas will be used to either produce electricity, or because the gas will be extremely hot, it can be used to produce other things. Like it can be used to generate hydrogen out of water, for example, things like that. And the pebbles themselves, they're manufactured in a way that they're very solid, and they have graphite which is a material that you need for many reactors. And yeah, I don't know exactly to what extent you want to know more about pebble bed reactors, but yeah, it's something that is being under development. Yeah, I can go here actually. So fusion reactor would be kind of this, but the opposite direction, and the atoms would be much lighter than this. So it would be like here you would have like deuterium or helium-3, and here as well. And then these ions have to be stick together, and then they produce something heavier that is more stable, and that liberates energy. It's more complicated because here in fusion you just shoot a neutron, and then the neutron triggers a fission reaction and generates more neutron. In a fusion reaction, you have to bring these two atoms very close to each other. And that's very hard to do because they're both positively charged. So you have to overcome a very, very high energy barrier here. But they're working on it. Actually, there is a project in France. They're building. They have been building a fusion reactor for many years, and it's supposed to work. It's just a matter of building it. Many countries are participating in the project. And so the advantage of fusion would be that, as I showed here, we have essentially infinite fuel for fusion reaction. What is it, like the 300, basically in seawater, we have so much deuterium that we will never lack energy. Now the helium-3 thing, so when the fusion reaction is happening, you have to keep the plasma very hot in order to keep the reaction happening. Let me put this one back again. And usually to keep the reaction hot, we throw like microwaves or so some sort of waves at the plasma to heat it up. And if that energy that we throw at the plasma is more than the energy we can extract, then the fusion reactor is not producing electricity. With helium-3, what happens is that the products of the fusion reaction are not neutrons, they're charged particles. So that charged particles are produced in a helium-3 reactor. It will interact with the plasma and it will help to heat it up. So once the reaction starts, it's easier to keep it hot without externally injecting energy into it. Whereas the other types of fusion reactions like deuterium, they produce neutrons, and some of the energy is wasted in neutrons escaping the reactor because they don't interact with the plasma. So in these reactions here, I didn't put all of the elements that are involved. So for the fission reaction, we have here uranium produces fission products. Some of these things are pretty radioactive, and that's the nuclear waste that we have to manage or do something about it that can be a little bit complicated. In the case of fusion, we don't have these kind of products that are created. So it's basically, the products are usually helium. Yeah, I think it's always helium or something like that. And it also produces neutrons, but that neutron will just fly away and be absorbed by something and then very quickly be stopped. So there is no production of harmful atoms as such. The only little thing is that on the walls of the fusion reactor, Those walls are going to absorb all of those neutrons coming out, and they're going to become a little bit radioactive. But it's very minimal compared to the kind of products in a fission reaction. There is no reason why it shouldn't work. They've done like all the calculations and everything, and it's not the first. It's not the first time they're doing fusion. We've done fusion many times in other types of reactors, so we know how to make fusion. We know it liberates energy. We know a lot of things about that. It's just that we haven't been able to successfully take more heat out of the fusion reaction than the heat that we put in. And for fusion reactors, especially that type of reactors like tokamaks, the size matters a lot when it comes to the stability of the plasma inside, and also just the amount of energy that we have to put in and the amount of energy that we can take out. So by making something much bigger, like the thing they're doing in ITER, it becomes much more feasible to actually harness energy out of that machine. So yeah, I don't see there is no reason why it shouldn't work. It's definitely going to work.